Hello, today me and my partner Fabio will be presenting our Chapter 6 chemistry overview. So first let's talk about intermolecular forces and London dispersion forces. So what are intermolecular forces? Well, intermolecular forces are forces that exist between atoms that includes the forces of attraction and repulsion, which act between neighboring atoms. Intermolecular forces are electrostatic in nature and are relatively weaker than intramolecular forces. Intermolecular forces differ from intramolecular forces because intermolecular forces are the forces between atoms, while intramolecular forces exist within an atom, or what holds an atom together. Intermolecular forces also have great influence over the physical properties of all substances. There are also various types of intermolecular forces. In order from strongest to weakest, they are ion-dipole forces, hydrogen bonding, dipole-dipole forces, and London dispersion forces. First, we will be discussing the weakest of them all, London dispersion forces. London dispersion forces are temporary attractive forces that occur when electrons of two different adjacent atoms occupy the same region of space and form temporary dipoles. London dispersion forces are weaker than all other intermolecular forces. Intermolecular forces also affect the properties of compounds. Different compounds have different intermolecular forces. When the molecular forces of a compound are strong, then more energy is required to break those forces. When they are weak, then they require less energy. Nonpolar covalent bonds, for example, only have London dispersion forces. Because London dispersion forces are so weak, the nonpolar covalent bonded compounds have relatively low boiling and melting points. And that will wrap up our discussion on intermolecular forces in relation to London dispersion forces.
Let's go ahead and move on to discussing dipole-to-dipole interactions, ion-to-dipole interactions, and hydrogen bonding. So as we already know, polar molecules consist of atoms with different electronegativity values that cause one atom to pull on the electrons of the other to a higher degree. This creates a partial charge on both sides of the molecule, with one having a partial negative and the other having a partial positive, with the side that has a more electronegative atom being the side with the more negative charge. Although it's not a whole charge, it's just a partial charge. So when the partial charges between two polar molecules attract each other when they're opposite charges, this forms an interaction that makes them come together, and these are known as dipole-to-dipole interactions. They're relatively weak since they're only partial charges, but are still stronger than London dispersion forces, since they're at least a partial charge, whereas in the London dispersion forces, it's just the movement of electrons that causes the attraction between atoms. So, and the strength for dipole-to-dipole interactions isn't quite based on size like it is in London dispersion, but rather than polarity. So the differences in electronegativity and electronegativity trends. Alright, so let's go ahead and now take a look at ion-to-dipole interactions. These interactions are similar, except that they're not between dipoles, and they're between an ion and a dipole, although the basics are still the same. So the charge on the dipole molecule is attracted to the opposite charge on the ion. And these are stronger because we have a whole charge and a partial charge rather than two partial charges. Although this is the strongest of all the intermolecular forces, this is still weaker than covalent and ionic bonds because we're still dealing with the partial charge. And the strength of this interaction is dependent on how big the partial charge and the whole charge is, similar to a dipole-to-dipole, except now this involves an ion. Alright, so let's move on to hydrogen bonding. So this is a type of dipole-to-dipole interaction, except that it involves specifically a hydrogen atom being bonded to a nitrogen, a fluorine, or oxygen atom. So this scenario is different from a usual dipole-to-dipole interactions because the electronegativity value of nitrogen, fluorine, and oxygen is so much greater than the electronegativity value of hydrogen atoms. This causes very large partial charges, and this is a partial charge that is closest to a whole charge. Due to this, it is much stronger than the usual dipole-to-dipole interactions. And although this is still not as strong as an ion-to-dipole interaction, since the ion-to-dipole still has one of the components having a whole charge. And these attractions are still very strong and are strong enough to pull apart ion lattices. Like in the case of water, where the hydrogen bonds, if there's a large number of interactions between the hydrogen bonds and an ion, then it's strong enough to pull it off due to the mere force, attractive force of this hydrogen bond. Although it is still not strong as those ionic bonds, If there's enough hydrogen interactions, it can still pull apart an ionic lattice, unlike dipole-to-dipole interactions. Now let's discuss how dipole-to-dipole interactions and ion-to-dipole interactions affect boiling points and solubility. So in terms of boiling points, the stronger the interactions, the higher the boiling points. This is because the stronger the molecules are together, the more kinetic energy that will have to be input into the system to make them split apart. For dipole-to-dipole interactions, this all depends on the polarity. So higher polarity is going to have a higher boiling point because the higher the polarity, the higher the partial charges are on the molecules. So the more attracted they're going to be to each other. Similar idea applies to ion to dipole interactions, except now will be the higher the ionic charge, the higher the boiling point. So now let's discuss solubility. For ionic compounds, the deciding factor whether the ionic compound will dissolve, and we'll be talking about specifically in water to help us understand this concept, is going to depend on how strong the ion to dipole interactions are versus the lattice energy of the ionic compound. So let's say we have an ionic compound in water. The water will attempt to make ion to dipole interactions with the ions in the ionic compound, and this is going to have to compete with the lattice energy of the ionic compound. But as I discussed earlier, the ions are going to have a stronger interaction between each other than there would be in an ion to dipole interaction. So the way that the water will still manage to dissolve the ionic compound is in the number of interactions. So there's going to be multiple water molecules attacking or being attracted to these ions. So in numbers, they can gather enough strength to split up the lattice. In the case of polar molecules, you're going to have dipole-to-dipole interactions in the solvent versus dipole-to-dipole interactions in the solute. In the case of water, you're going to have the hydrogen bonding, which is a type of dipole-to-dipole interaction, and hydrogen bonding is stronger than other dipole-to-dipole interactions, so they're going to be strong enough to split up the polar molecules. In a case where we're not dealing with water and we're dealing with another solvent, it will all depend on whether the dipole-to-dipole interactions of the solvent are stronger than the ones in the solute. So the main factor for solubility are the number of interactions going on and the strength of the interactions themselves. So now let's talk about why nonpolar molecules won't dissolve in polar molecules. So this is due to nonpolar molecules having different intermolecular forces than polar molecules. So from polar molecules, you have dipole-to-dipole interactions. And then for nonpolar molecules, you have London dispersion forces. So this is like having apples and oranges. They're just too different to dissolve in each other. This also means that nonpolar substances can dissolve in another substance. It just requires the solvent to be nonpolar and to have stronger London dispersion forces than the solute nonpolar substance.
Now we will discuss phase diagrams and the unique and unusual properties of water. First and foremost, what is a phase diagram? Well, a phase diagram is a graphical representation depicting the physical states of a substance under different conditions of temperature and pressure. So why specifically are temperature and pressure chosen? Well, the pressure that surrounds a substance can affect states of matter because pressure applies forces on substances which allow them to be more compact and held together. So when the pressure increases, more energy is required and freezing and boiling points increase. When temperature increases, molecules and atoms have more kinetic energy and allow substances to more readily change state from solid to liquid or liquid to gas. Now if we take a look at a phase diagram, we can see that it is divided into the three states of matter: solid, liquid, and gas. Then we have the triple point, which is the point where the temperature and pressure where a substance can coexist as a gas, liquid, or solid. Then we have the critical point, which is the point where the two phases of a substance cannot be distinguishable from each other. This is where density of a liquid and vapor are equal and thus form a supercritical fluid. Now onto the special properties of water. Because of the hydrogen bonds that exist in water, water has a large boiling point. This is because a large amount of energy is required to break those hydrogen bonds before water can freeze or boil. As a result of water having such a large range to exist as a liquid and can be very slow to freeze or boil, it allows ecosystems to thrive. If water was very easy to freeze or boil, drastic changes in the environment, such as oceans or lakes, would cause all the organisms living in the water to die. Then there is surface tension. Water has high surface tension due to its hydrogen bonds. This allows things to be placed on the surface of water despite density. Many organisms, such as insects, use surface tension to walk on water without sinking. These organisms are able to do so because the force they apply on the surface of the water is not enough to break the hydrogen bonds of surface water molecules. Water also has a high heat of vaporization. This property of water is beneficial to the ecosystem because it helps moderate the temperature of the ecosystem. The quantity of heat that is required to convert a unit of water into its vapor form is very high because of the hydrogen bonds found inside water. Then there's viscosity. The viscosity of water measures its resistance to flow and is critical to many of its functions. The low viscosity of water is important in its role as a solvent for life's chemicals reactions and for blood circulation. Water's cohesion, which are the attractive forces that allow molecules to stick together, also make it unique. The cohesion of water molecules helps plants take up water at their roots through capillary action and helps animals regulate body temperature. Water is also a universal solvent. Because of water's polarity, it is able to dissolve or dissociate many particles. Oxygen has a slightly negative charge, while the two hydrogens have a slightly positive charge. The slightly negative particles of a compound will be attracted to the water's hydrogen atoms, while the slightly positive particles will be attracted to water's oxygen molecule. This causes the compound to dissociate. Finally is water's density. For all substances, they become less dense when they are heated and more dense when they are cooled. However, water only continues to become more dense until it reaches 4 degrees Celsius. After it reaches 4 degrees Celsius, it will become less dense. When freezing, molecules within water begin to move around more slowly, making it easier for them to form hydrogen bonds and eventually arrange themselves into an open crystalline hexagonal structure. Because of this open structure, as the water molecules are being held further apart, this makes water's liquid state more compact than its solid state and explains why ice is able to float on water. Ice at the top of a body of water serves as an insulator and allows life in water to survive. Thank you for listening, and that will include our Chapter 6 overview.